Hello, everyone. My name is Juhee Kim. Today, I'm going to talk about our research bypassing ARM's memory tagging extension with a side channel attack. First, I'm a PhD student at Seoul National University, and my research interests include general software system security, focusing on finding bugs and developing mitigations. And this research was conducted in collaboration with Jin-Bum Park and Tae-Soo Kim from Samsung Research and people from Seoul National University, including my advisor, Byung-Young Lee, and my colleagues, Hyun Ro, Jae-Young Chung, and Young-Jo Lee. In this presentation, I'll first introduce the new ARM's memory tagging extension and how it works. And then I'll explain the MTE tag leakage side channel we discovered from the Google Pixel devices. And finally, I'll present the real-world MTE bypass attacks in Google Chrome. By the way, we've disclosed our paper before, and it was introduced by Low Level Learning and the Prime Time on YouTube. And their videos are awesome, so please check them out. Let me begin with ARM MTE. Memory corruption attacks have been the most common and severe threats in software systems. In 2014, Heartbleed affected millions of servers by exploiting a buffer overflow vulnerability. Last month, regression was discovered, which can compromise any SSH server. Pathfinder and BlastPath also enable zero-click attacks on Android iOS devices. So what is memory corruption? Normally, a program accesses memory objects through pointers. And if the pointer points to an object that is intended to point to, the memory access is valid. However, if the pointer points to an out-of-bounds memory region, the access is invalid. Or if the object is freed and the pointer is dereferenced after that, the access is also invalid. So since the early days of buffer overflows, attackers have developed sophisticated techniques like return-oriented programming, and in response, defense mechanisms like stack canaries, ASLR, and CFI have been developed. And in recent years, hardware-based defenses like Intel MPK and ARM pointer authentication has been introduced. And last year, ARM introduced memory tagging extensions, so-called MTE. And Google Pixel 8 and 8 Pro are the first MTE-enabled devices. MTE has been a hot topic in the security community. Companies like ARM, Google, Microsoft, and not to mention the academic security researchers have been anticipating MTE to be a game changer in the security field. So why is MTE so special? It's because MTE is a hardware-based memory corruption detection, so it is fast and compatible, requiring minimum effort to adopt. MTE basically operates with a lock and key mechanism, ensuring that only a valid key can open the lock. Each pointer contains a key, and each memory object contains a lock. And MTE ensures that only the valid pointer can access the memory object with the matching key and lock, and prevent other invalid memory accesses. And to achieve this, MTE introduces memory tagging. For memory tags, a dedicated memory region stores a 4-bit tag for each 16-byte data. And a pointer stores the tag in its upper unused bits. This is possible because the address space are usually around 48 bits, and the top bits in the 64-bit pointer are unused, so ARM uses that space to store the MTE tag. And ARM introduced new MTE instructions to create a random tag and load store memory tags. So using these instructions, a program can assign a random tag to each object and the pointer. Finally, when the program accesses the object through a pointer, the MTE hardware checks whether the pointer tag matches with the memory tag. On a valid access, the tags match and no fault is raised. On an invalid access, the tags mismatch, and the CPU raises a tag check fault, which crashes the program. Now, to exploit a memory corruption vulnerability, attacker would need to bypass the MTE. How do we bypass MTE? One way is to exploit tag collision. Since the tag is only 4 bits, there are 16 possible tags. So if the objects are randomly tagged, there is 1/16 chance that 2 different objects have the same tag. And the attacker can wait until the tags collide and trigger the memory corruption. Another way is to corrupt the pointer's tag. So if the attacker can corrupt the entire 64-bit pointer, the pointer's tag can be set to match the target object's tag, so it can bypass the MTE. Here, the biggest challenge is that the memory tag is randomly created at runtime, and the attacker does not have any knowledge of it. And without knowing the memory's tag, the memory corruption is not reliable anymore. On brute force attempts, the program would crash 15 times out of 16, so the success rate would be around 6%, which is too low to be useful. So therefore, we need a successful MTE bypass. We need a reliable way to leak the tag of any address for a successful MTE bypass. To solve this, our approach mainly leverages 2 common CPU features. First, we exploit cache to leak the tag track results with a cache side channel. Second, we exploit speculative execution to avoid crashes. So to understand our attack, let's first take a look at the cache side channel. Cache is a small and fast memory that stores recently accessed data. It is located between the CPU and the main memory. And when the CPU accesses a memory object for the first time, it fetches the object from the slow main memory. Then it stores the object in the cache, so the memory access is slow. When the CPU accesses the same object again, it fetches the object from the cache, so the access is fast. So with this timing difference, we can construct a cache side channel. It simply measures the time to access the memory. So if the measured time is fast, it means that the object is cached and has been accessed before. If the measured time is slow, it means that the object is not cached and has not been accessed before, loaded from the slow main memory. So we can exploit cache side channel to leak whether an address is accessed. Next, we exploit one of the most common CPU optimization called speculative execution. So what is speculative execution? Assume the CPU executes a code in the left side and is currently running the line pointed by the arrow. On the right side, the CPU contains a pointer that points to an object. And since the CPU has encountered an if statement here, it needs to decide whether to take the true or false branch. If the condition value is unknown for a long time, waiting until it's ready would be a huge waste of time and CPU resources. So the CPU leverages speculative execution to speculate on what will happen next, instead of waiting this condition value. So the CPU speculates that this condition is true and executes the true branch. And on this load instruction, the CPU would dereference the pointer and check the pointer's tag with the memory tag. And here we assume a tag match. Then the memory object is loaded into the CPU. But since it is loaded by a speculative execution, the CPU holds the loaded data into a speculated state. And when the condition value is later ready and it is actually true, the speculation is correct, and the CPU confirms the speculated state to the actual evaluated state. Then it continues the execution. However, when the condition value is false, this code shouldn't have been executed. So the CPU discards this speculated state and reverses the execution to the correct path and continues with the false branch. However, the CPU does not revert the cache state, so the memory object is still cached. So what if a tag track fault occurs during the speculative execution? Assume the CPU speculatively loads this invalid pointer, and this pointer tag does not match the memory tag, so the CPU raises a tag track fault. However, this fault does not crash the process immediately because it is raised during speculative execution, and there's a possibility that the code shouldn't have been executed. So when the condition value arrives and it is false, the CPU reverts the tag track fault and the execution. So this means that the tag track fault does not crash the program in the speculative execution. So by exploiting speculative execution, we can now trigger tag checks, either for tag match or mismatch, but never crash the program. Now, combining side channel, cache side channel, and speculative execution, we can construct an MTE side channel attack. In this attack, the goal is to leak the memory's tag. Assume we have this track pointer that points to a track object, and we want to leak the memory tag of this object. To leak the tag, we are going to access this track pointer in two cases. Case A with a valid tag, case B with an invalid tag. And then we're going to see if there's any cache difference between the valid and invalid cases, so that we can determine whether the pointer contains a valid tag or not with the cache side channel. However, if we simply access the track pointer, both cases would cache the object regardless of whether the tag is correct or incorrect. So there is no cache difference between them, so cache side channel will tell nothing. But what if we add additional memory access, say a test pointer? Will there be any cache difference? To verify this, we were going to run this code shown on the left, which triggers speculative execution. And in case A, where the tag is valid, in the track block, the CPU speculatively accesses with the track pointer. So the track object is loaded to the cache, and the CPU matches the memory tag. And here the track passes, so the CPU proceeds with the next instruction. And the test object is also loaded into the cache. And the tag track, of course, passes. In the end, when the condition value is later evaluated as false and the CPU reverses the execution, and the cache would contain both the track and test objects. But in case B, where the pointer's tag is invalid, the CPU speculatively accesses the track pointer, and here the CPU raises a tag track fault, and the CPU does not have any reason to proceed the speculative execution. Because if it was a correct speculation, the tag track fault would be synchronously caught by the CPU, and the next test block will not be executed. If it was a wrong speculation, the CPU would revert the execution anyway. So it is possible that the CPU stops the speculative execution here. If so, when the condition value is evaluated as false, and the CPU reverses the execution, the cache would contain only the track object. So now the cache side channel comes into play. In case A with a valid tag, the cache contains both the track and test objects. In case B with an invalid tag, the cache will contain only the track object. Therefore, if we measure the time it takes to access the test object, the time would be fast in case A, but slow in case B. From this difference, we can leak whether the tag in the track pointer is valid or invalid. And the key question is whether these new MTE chips actually contain the tag leakage side channel. Previously, an attack called Pac-Man leaked ARM pointer authentication code with side channel. So it is possible that these new ARM chips also have the similar side channel issue with MTE. Google Project Zero actually conducted an analysis on this MTE hardware, including the search for the tag leakage side channel. But they have failed to find such side channels. They have tested code consisting of a track pointer load and a dependent test pointer load, varying the distance between them, but this did not generate any cache difference on the test pointer. What we did was finding out what should be in the green part to induce the cache difference between the valid and invalid tags. And as a result, we identified two memory access patterns that actually create such differences, which we refer to as tag leakage gadgets. And we also have suspected hardware root causes, and you can find more details in our open source code and our archives paper. And on another research group, VUSAC also orthogonally discovered one of our tag leakage gadgets. And ARM equally acknowledged the discovery from our group and VUSAC. So our first gadget contains multiple loads in the track block, and this task block can be any memory access to task pointer. I think P0 was so close because they have tested only one load, but actually at least 2 loads were required for the side channel. So when the tag track fault occurs multiple times, the following instructions are not executed, leaving task pointer not cached. For the root cause, as ARM has not disclosed any hardware side details, we conducted additional experiments and reviewed the relevant documents. And we suspect that on multiple faults, the CPU re-speculates that the previous speculation was wrong. In other words, if the CPU experiences too many faults, it considers them as an indicator of the wrong path and stops or reduces the speculative behaviors. This root cause is based on the relevant patent filed from ARM Limited, and our paper also provides the experimental results supporting this conclusion. And the second gadget triggers the store-to-load forwarding behavior in the CPU. In the check block, it stores a value to the check pointer and then immediately loads this value from the check pointer. In this case, the CPU optimizes the performance using internal buffers like this to log recent stores and load instructions. If a store and the following load instruction is for the same address, the CPU directly forwards the value from the store to load instead of accessing the cache. So, and after the store to load behavior, the task block accesses memory access dependent to the value forwarded in the check block. And we've observed that when tag track fault occurs during store to load forwarding, either in the load, store, or both instructions, the dependent memory access in the task block is not executed, meaning that the data is not forwarded. And we suspect that the root cause of this is the CPU blocking the store-to-load forwarding on faults to mitigate other side channel issues. Now, based on the MTE side channel gadget, we can construct real-world MTE bypass attacks. Since MTE has been recently become available, not many real-world software systems actually use MTE for attack mitigation yet. But widely used softwares like Android, Chrome, and Linux kernel, they already provide an optional MTE support. And also some secure operating systems utilize MTE to mitigate memory corruption attacks. And we think more software vendors will adopt MTE in the near future due to its benefits. So we assumed that MTE is already enabled, and we developed real-world gadgets and MTE bypass attacks on 2 major systems, Google Chrome and the Linux kernel. In this talk, I'll only present the attack on the Google Chrome V8 engine, which constructs a tag leakage gadget from JavaScript code and leaks the MTE tag of the entire renderer memory. We also found the gadget from the Linux kernel and developed an attack. So if you're interested, please refer to our paper. So let me first introduce the threat model of Google Chrome, especially the renderer process. The renderer process consists of the V8 JavaScript engine and the Blink rendering engine and other third-party libraries. And attackers can provide malicious data, malicious JavaScript data, HTML, CSS data. And they can trigger memory corruption vulnerabilities in each code base. But since the JavaScript code is directly compiled and run by the V8 engine, it has been the most accessible targets for the attackers. So the VA sandbox is developed and it is applied by default to sandbox the untrusted JavaScript code execution. And it ensures that no JavaScript can access the rest of the memory. However, the Blink render and third-party libraries also contain a vast amount of code, potentially containing memory corruption vulnerabilities, so attackers can still exploit them even if the VA sandbox is enabled. And as we assume the MTE is enabled, the Chrome randomly tags the object in Blink and third-party libraries, so it does mitigate the memory corruption on those code bases. But although the VA sandbox prohibits JavaScript from directly corrupting these objects, if you can somehow leak the MTE tags of the renderer memory, we can bypass MTE and exploit memory corruption vulnerabilities. So this is our gadget number 2 created using JavaScript. Since this is a JavaScript code, the attacker can provide anything, including the code, array, and indexes. First, the attacker prepares a 64-bit out-of-bounds index, and a check array is accessed with this index so that it can represent the attacker-controlled check pointer. Of course, the V8 would detect this out-of-bounds array access and raise an error if it was a normal execution. But as you wrap this access in an if statement and trigger a speculative execution, the V8 would not raise an error. But the CPU actually accesses an out-of-bounds address in the speculative execution. Therefore, the gadget can trigger a store-to-load forwarding with the check pointer, and the forwarded value is used as an index of test array. In this way, the test array, we're going to become the test pointer and constructing our gadget number 2. And to exploit this gadget, the attacker can construct a tag leakage function like this, which leaks the tag of an arbitrary target address. The function iterates over all possible tag values from 0 to 15. Then it creates an out-of-bound index for the tag value and the target address. Then the function triggers the speculative execution with the tag leakage gadget. Here, depending on whether the tag is valid or invalid, the test array will be either accessed or not. And then the access latency of the test array is measured. And the function returns the tag with the minimum access latency, which means it's going to leak the tag value. And leveraging this tag leakage function, the attacker can bypass MTE in Google Chrome. The strategy is quite simple. First, with the tag leakage function, it leaks the tag of the memory object. Next, trigger memory corruption attacks if the tags are going to match. And in this example, we assumed a heap overflow vulnerability that a vulnerable object is overflowed to a neighboring target object. And in the following slides, I'll explain the attack in more details. First, the attacker leaks the tag of the vulnerable object, and then leak the tag of the target object. If the tags do not match, we're going to reallocate the target object, and then leak the tag again. If they match, now we can trigger the out-of-bounds memory access. The tag check would pass, so the attacker can successfully bypass MTE. So we've created a demo. In this demo, I used a real-world vulnerability in Google Chrome, a heap overflow in libbpx library. First, I'll show the original memory corruption vulnerability. It allocates the object right after the vulnerable and target object right after the vulnerable one, and trigger the heap overflow, and the process immediately crashes due to the tag track fault. Next is with our MTE tag leakage gadget. Once the objects are allocated, we leak the vulnerable object's tag and the target's tag, and target is reallocated until its tag value matches the vulnerable object's tag. And then we triggered the heap overflow. This time, there was no crash. And you can see that the target address was B200, and we actually wrote to the address B210, 30, and 50. So the vulnerability was successfully triggered without a crash. So we reported this issue to relevant vendors. First, ARM acknowledged the MTE tag side channels in multiple ARM cores. However, they stated that MTE tags are not actually considered as a secret in their architecture, so tag leakage side channel is not a security vulnerability. But still, they expected the cost of the hardware fix to be low and recommended the CPU vendors to fix it. Google Android security team has acknowledged the MTE tag leakage issue as a hardware flaw of their Pixel devices. Still, they consider MTE as a strong mitigation against side channel attacks, against limited shot exploits where side channel attack is not possible. Google Chrome V8 security team concluded that the MTE side channel attack does not violate the V8 security model because data confidentiality, including MTE tag, is out of scope of their V8 sandbox. And they also mentioned that they currently do not have any plans to adopt MTE on renderer due to potential side channel issues like the one we presented. But actually, we think V8 can mitigate this side channel issue by fixing their sandbox a little bit, which we describe in our paper. So as a takeaway, ARM memory tagging extension is a promising security feature to defend against memory corruption attacks. No previous defenses have been able to provide this level of security and efficiency. However, we have shown that current MTE hardware contains tag leakage side channel issues, and we hope MTE-based security can be further improved by adopting software and hardware enhancement in the future. So thank you for listening to my talk. If you have any questions, you can reach out to me through this email or send a message to me through the app.